So I'm very pleased this week to introduce Eve Armstrong. So Eve has a background in physics, but also, unlike most of us, has a much richer background than that. So she's also has an arts degree and has some experience in theater. She has worked on a wide range of applications of machine learning and similar nonlinear fitting processes in physics, in astrophysics, particle physics. But also she's worked on neuroscience and worked with people investigating birdsong, for example. Today, she's going to talk about applications of some of these deep learning type techniques to neutrino physics and also to some other things. So it's all yours, Eve.
Thank you, Douglas. Thank you for the invitation. Thank you all for coming. Let me share my screen and move to full screen mode. Douglas, have I successfully broadcast an image of the Crab Nebula?
Yeah, it's good.
Wonderful. So as Douglas said, I am going to talk to you today about a procedure called inference, which you might know by the name of machine learning or optimization. And Douglas has told me that I should aim for a rather broad audience. So I'm going to talk about applications of these kinds of techniques to a range of topics. And I'm going to start with neutrino flavor evolution, and I'm going to begin by introducing you to this image that you see in the background. This is the Crab Nebula. It's the remnant of a supernova, the death of a supermassive star that was actually observed to occur by the Chinese in the year 1054 AD. The Chinese saw what they called a new star, a nova, appear in the sky. And they thought that a new star was being born, but what they didn't realize was they were seeing a star dying. So previously, the brightness of the star was too faint to see by eye, but the explosion's orders of magnitude brighter than that. So they were suddenly seeing the explosion, and we're seeing the remnants of this explosion 1,000 years later. This is an enormous cloud of expanding gas. And the color you see here is what we call false color. We're not trying to pull one over on you. By the name false. What I mean is that the color codes for something other than color. And here it codes for the elements that you see in the cloud. So I don't remember exactly what the colors are, but for example, the blue codes for oxygen, and the carbon might be the orange, and silicon might be the yellow. And these elements were created during the nuclear fusion process that happened while the star was main sequence star before it exploded. And now these elements are expanding out into interstellar space to become the building blocks of other things like us. We are star stuff, you might have heard. It's true. So I'm first going to start off applying an optimization procedure to understand how neutrino flavor evolution occurs in these supernova events. And I understand, again, this is a broad audience, so I won't assume everybody knows what neutrinos are or why you might care. So I'll start off by explaining what neutrino flavor is. Then some problems with understanding how neutrino flavor evolves in these events. Oops, sorry. How inference or optimization might help us with these problems, and what we're going to be working on next. So we start with a main sequence star, a supermassive star. And by supermassive, what I mean is a star with a mass at least 10 times the mass of our sun. This star, during its main sequence lifetime, is fusing the elements that we know of from helium all the way up through iron in its core. So first it takes 4 hydrogen nuclei, fuses them into helium, and that's an energetically favorable process. So it releases light that we can see. That's why we see the sun shining. Then it takes the helium it's made and fuses that into carbon. And you march on up through oxygen, silicon, magnesium, all the way up to iron. And then you get to iron, and it is no longer energetically favorable to fuse iron into the next heavier thing. And so the star loses the battle that it's been having ongoing for millions of years with the inward pull of gravity. The radiation pressure due to its release of light from this fusion process has been sustaining it under the force of gravity. But now, once it gets to iron, it's out of fuel. It can't fuse iron into anything heavier. So the only possibility left for it is to collapse. catastrophically under the force of gravity from a radius of about 10 million kilometers to a radius of about 10 kilometers within about a second or two. So we're talking about the cross section of, say, Vancouver. I understand most of us here are from Vancouver. Now think about that. Gravitational binding energy released from by an object that is collapsing from 10 million kilometers to a radius of 10. 99% of that gravitational binding energy is released as neutrinos. And you see 3 of them escaping from Vancouver here. One is the subscript on the neutrino is code for its flavor. And I'll get to what flavor means in a moment. There are 3 known flavors of neutrino. One is electron flavor, one is mu flavor, and one is tau flavor. And what these neutrinos do as they are fleeing out from this collapsing core, they're pushing out the outer envelopes of the star. Now, you can think of the collapsing star as kind of an onion where you've got this compact iron core, but then layers of unfinished fusion products. You have a very thin layer of hydrogen that never wound up getting to helium. You have a layer of helium, carbon, oxygen, and so forth. And the neutrinos, as they expand out from the collapsing core, they push out these elements. That is what you saw in the introductory slide. And so these elements that are floating around in space now become the building blocks of new objects. But hang on, we look around and we see that there are other elements. There are elements heavier than iron, right? There's Hg, mercury, sorry, forgot for a moment. There's mercury, gold, plutonium, uranium. Where did they come from? And further, the physics of these explosions is not that well understood. And it turns out that both these questions relate to this concept of neutrino flavor. And here's what flavor means. It defines the manner in which neutrinos interact with the matter in this expanding cloud. And for example, I'm showing you an equation here where an electron flavor neutrino captures on a neutron and produces a proton and an electron. So the flavor of the neutrino is named after the lepton that's produced in this process. But what you might find more interesting here is look what's happened. A neutron is transformed into a proton. And the neutron to proton ratio in any local environment is going to set which elements can be created in that environment. So we wonder which elements can be created in these core collapse supernova. They are candidate sites for the creation of the heavy elements. So we would like to understand processes like these better, the manner in which the neutrinos interact with the expanding matter in the cloud. There, that's the introduction to why you might be interested in neutrino flavor. So now on to problems. It's a gnarly problem trying to understand what the flavor field looks like inside this collapsing core and the envelope we call the envelope the expanding shells. As I just said, flavor in part dictates the physics of these explosions. Now, under normal circumstances, that is circumstances we're used to, neutrinos interact extremely weakly with matter. They have masses around 10 to the minus 6, 10 to the minus 9 times the mass of an electron. They're little. Hold up your hand. Wait a second. About 1 trillion neutrinos just went through your hand. They zip through the core of the Earth, no problem. But at the densities we're talking about, at the cores of these supernova, the interaction with matter is significant. The densities are that high. And as I said just a moment ago, flavor can in part set the neutron to proton ratio. So these supernova are candidate sites for the creation of some R process elements. R process elements are some of the elements heavier than iron. I'll leave it at that for now. But the flavor evolution is not, it's a nonlinear process, very difficult to study with current computational techniques. And here's what I mean by that. First of all, a neutrino's flavor is not a static property of a neutrino. If it's emitted as electron flavor, that does not mean it's going to still be electron flavor a kilometer away. In particular, the flavor will change with every interaction with any other particle, including other neutrinos. So in that way, we have a nonlinear problem. And then in addition, the neutrinos don't just stream from radius 0 out to our detector. smoothly. There's backscattering, there's direction changing, energy changing backscattering, whereby flavor states at later or larger radii can impact flavor states at shorter radii. So it's a fiercely nonlinear beast, and current simulations of supernova, I'm gonna kind of gloss over these next few bullets because I'm going a little bit long here. But current simulations omit very important aspects of this nonlinearity, due in large part to the complexity of these codes. So say, for example, you wanted to investigate one particular question, one particular theory about flavor evolution that has not yet been posed. It could take you, say, a year, maybe 2 years, to rejigger your code so that it can look at that specific scenario, and then that specific scenario might not have turned out to be useful for your particular purposes. I'm talking about parameter regimes of possible interest, for example. Skip over that one. I just basically said that. You don't have to reread it. So how about this? To augment these integration techniques, these very, very powerful techniques, how about an alternative formulation called inference, or you might know it as machine learning. Machine learning is a kind of subset of inference. It has the properties, some desirable properties for our purposes, where it's integration blind. I mean, or you can formulate it as an integration blind technique, I should say, where it doesn't know about direction. So forward, backward is not a problem. It can very efficiently search a vast parameter space, ruling out regions that are highly unlikely to be relevant to your problem and homing in on regions that are highly likely to be interesting and to which you would like to point your existing large-scale, high-powered codes. And finally, it can be designed for sparse data sets. We are going to be dealing with sparse data sets. If we ever get another signal from a galactic core collapse supernova, we will have not a time series, but one location, right? We have a detector on Earth. We can't cram our detector out into the supernova envelope to gather a measurement of the flavor state there. Okay. So we want to find a technique that is designed to squeeze as much information as possible out of a very sparse set of measurements. Okay, so here's the nonlinearity that I'm talking about. This is a toy model in that we're talking about 2 neutrino beams emanating from this neutrino sphere, which you could think of as the surface of last scatter from this core. It's a toy model in that there are 2 neutrino beams as opposed to, say, more like 10 to the 58 for a realistic event. They stream into our detector on Earth through this matter-dominated region. This is the supernova envelope. And with forward scattering only, as you see in this picture, there's no backscattering yet. The steady state evolution, so there's no time here, there's just radius for now. It can be evolved forward in one direction. So no problem for forward integration, or backward. If you have a flavor measurement at your detector, you can integrate backwards and infer the flavor state at every location backwards along the path, which is what we want to be able to do. And down here, for any of you who study this, you see the evolution of the density matrix rho in terms of the radius r as a function of the very smooth Hamiltonian h. Okay, but that's not what happens. You have backscattering events happening all over the place where, look, neutrino 1 undergoes a direction changing event, perhaps an energy changing event as well, prior to entering the detector. So now, for those of you who know about this, we have added a collision term to the evolution of our density matrix. And this can significantly affect the flavor state throughout the entire envelope. I mean, the path really looks something more like that, okay? And we are going to be able to measure a flavor at our detector. And what we would like to do is measure the flavor at every location prior to that for every neutrino. Now, we're working with a toy model with 2 neutrinos for now, but in a realistic model, again, there will be around 10 to the 58 neutrinos released from these events. So here is what we've done. I'm going to give you an overview of what we've been working on for the past 4 or 5 years now. We began with a proof of concept. And what that means is we're working with a model in which there is no backscattering yet. It can be solved simply by forward integration. No problem. You don't need an inference procedure to solve this problem. So why bother? Well, before unleashing optimization on a problem that we don't yet know the answer to, we need a proof of concept that it can reliably give us back the answer we already know. Okay, so we have the answer from forward integration, and we want to get that answer back. So that's what we're doing here. So for those of you who know about this, I want to show you what the model looks like. We have the evolution of the polarization vectors, P sub I, after decomposing the density matrix into bases of polyspin matrices. So we have Px, Py, and Pz for each neutrino. We have a vacuum term, flavor will evolve even in a vacuum. We have an interaction term with a term that represents interaction with the matter in the cloud for each neutrino beam. And then we have a term that represents the interaction, the neutrino-neutrino coupling interaction. And what, for those of you who do not have any idea what I'm talking about, here's all you need to know for the purposes of today. In a two-flavor model, we have electron flavor, and then the other two flavors are lumped into X flavor because they're not really important at the energies we're talking about. So we have electron flavor and X flavor, where in the language of polarization vectors, Pz equals +1 for pure electron state, and it equals -1 for pure X state. Now, say all of the neutrinos are emitted from the neutrino sphere as pure electron flavors state. They will undergo a very efficient, what we call a resonance or a transition at some location within the cloud to pure nu X. For those of you who know a little bit about quantum mechanics, this is because the energy or mass eigenstates of neutrinos are not the same as the flavor eigenstates. And the electron flavor neutrinos pick up an effective mass as they travel through the cloud, encountering the electrons in the cloud. That's the bare bones reason for this transition. That's all you need to know for the purposes of today. Our question, it's called the MSW resonance for anybody who wants to look it up. Our question today for the inference procedure is the following. Where, at what location in the cloud does that happen? Can you give us that back? We know we can forward integrate, we know, it's no secret, but we want to challenge the inference procedure to give us that answer back, simultaneously with any parameters that we choose to leave as unknown in our model. So that's the challenge for this inference procedure. Now, what is this inference procedure? We use a specific formulation. It's called data assimilation, statistical data assimilation. I hid the name from you until now because it's a horrendous name and I wanted you to show up to my talk. But there you go. This is what it's called. It's an inverse formulation. It's designed to optimally combine a model with sparse data. So that's its most defining factor, sparse data. And in simulations, it offers a systematic means to identify which measurements you need to make to estimate any unknown model parameters to some desired precision. And I have this balloon down here because data assimilation was invented for weather prediction. So say you, in simulations, you identify the measurements you need to make some prediction of some duration or some strength, and you look around and there's no instrument that can measure that thing. So you say, okay, let's build it. This is the way in which new instrumentation has evolved. I actually came into contact with data assimilation during my work on biological neuronal networks. Douglas just briefly mentioned that in the beginning. I was using inference to estimate the synaptic strengths of neurons in a very, very tiny biological circuit. I should say one thing about the difference between this technique and machine learning, which I think is a word that people are much more familiar with. Two key differences, and I'm open to anybody else highlighting others that I haven't thought of. One is that with data assimilation, you're assuming that any measurements you make, any observations you make are due to some sort of underlying dynamical physical model that you can model. With machine learning, that's not always the case. Sometimes you just want an answer, you just want to know the answer, and you don't really care necessarily why the answer is what it is. Secondly, machine learning usually deals in large data sets. There's tremendous power that can be harnessed from large, dense data sets, for example, for the purposes of pattern recognition. And as I said, this technique is specifically designed to squeeze as much information as possible out of very sparse measurements. So here's what I mean by an integration blind procedure. we use an optimization formulation. And what I mean by that is we're minimizing a cost function. Or for those of you who aren't familiar with that language, we are seeking to punish an algorithm for deviating from a set of rules. That's another way you can think about it. So here we have a cost function that's nicknamed A0. I'll explain why in a moment. And we have two what I call error terms. Let me start with this one because I think it will be very familiar to most of you. This is your standard least squares measurement error that I assume you've seen before, where the Y sub L are your L measured quantities. And your X sub L are the associated variables of your model that are corresponding to those quantities. And so when you're subtracting Y from X, and what you're asking the algorithm to do is minimize that difference and penalizing it from deviating from 0. So in the language of our model specifically, we are measuring, this is what we're measuring. We're measuring PZ only because PX and PY are imaginary quantities. We'll never be able to measure them. PZ only of both neutrino beams only at our detector. And from those measurements, we would like to infer backwards the entire flavor evolution history. Can we do that? That was a big question we had when we first set out. This model error, we also want to penalize deviation from a model. Okay, so this is the manner in which data assimilation is simultaneously optimizing measurements and model. X dot minus f of x, where f is our model that I showed you a few moments ago, the differential equations and the polarization vectors. And I want you to notice that f is a function of these unknowns. So the unknown states x, vector bold x, is the complete flavor evolution history that we're seeking to predict. And the p are the unknown parameters, any parameters of the model that we're choosing to say, we don't know, and we would like to estimate. RF and RM in the blue, these are relative weighting terms. Now, this is important. We're seeking to minimize a cost function, which is pretty easy if the surface is convex. That is, if the surface looks like this, if you look at my video for a moment, there's one minimum, there's one global minimum, pretty straightforward to find that. But the surface is not that way because of the nonlinearity that's encompassed in the model. Okay, so the surface actually is riddled with local minima, maybe hundreds to thousands to millions of them in large machine learning problems. And if you fall off into a local minimum, very hard to scramble out of there and eventually get to the global one. Okay. So if you start in that space, you're lost from the beginning. So we don't start in that space. We start in a space where RM is much, much greater than RF. We're ignoring the model, we're ignoring the nonlinearity. So we're starting in a convex space and we're getting an estimate of the global minimum there. And then we stay there, hang on, stay there for a second, crank up the weight of the model error slightly so that you're imposing a little bit of model constraint, little bit of roughness on your surface. And the idea is, let's try to stay as close enough to the global minimum along the way so that we don't fall off into a local minimum as the surface becomes increasingly well resolved. So we crank up RF gradually by an incremental increase in beta. We have RF naught, which is a very, very tiny number, times alpha, which is a number slightly greater than 1, like 1.5, to the beta. So we're incrementing in the exponent there. And I want to emphasize this. So in minimizing both terms simultaneously, this is how we are squeezing information from the measurements, propagating them to complete these unknowns of the model. And the reason we call this cost function A is that you can actually derive this particular cost function from the notion of the classical definition of the action on a path in a state space, where the path of least action corresponds to the correct solution. So let me show you what I mean by that. We initialize many paths in our space to do this search. And by path, what I mean is an initial set of guesses. So a set of initial conditions on every single state variable at every location along our path. And then we let that path go and see whether it eventually finds its way to the global solution. Path 1 on the left, you see, so on the y-axis, we have the log of the action, and the cost function, in other words, and on the x-axis, we have our annealing parameter, beta. So we start off again at very, very high measurement error compared to model error, and then anneal in the model error. And the geography or the geometry of the surface is changing, but eventually this path drops to a low number, which you can calculate a priori is the path of least action, 10 to the minus 3 for our case, and it stays there. So this path has found a solution that is consistent with both the measurement and the model. On the other hand, and your hope is that all of them do that. But you see the path 2 does not. Path 2 apparently gets stuck in a local minimum along the way and gets lost forever. The error increases indefinitely. And this is an incredibly useful litmus test for identifying which paths found the correct solution. You don't have to look at the solutions corresponding to these guys. They're not right. All you need to do, all you're interested in is looking at the solutions corresponding to the paths that look like this. And here's what I mean by the solution. I mean the series in radius of all your state variables, px, py, pz for neutrino 1, px, py, pz for neutrino 2. And I think you can see that the path that found the global minimum comes much closer to pinpointing the location of the MSW resonance than does this one, where what I'm showing you, I'm sorry, I should have said this, the model, the true forward integration solution is the blue dotted line. And the prediction from the optimization is the black are the unmeasured states, and the red are the states that are measured, again, only at the detector. And perhaps at various locations in the interim, we experimented with how many constraints we had to put on the procedure in order for it to succeed. So 7:30, okay. General findings, I'm going to go through this rather quickly. So with a partially known model, and what I mean by that is any parameters of the model are unknown. Constraining flavor only of the detector permits a high degeneracy of solutions. That is, multiple solutions are possible. That's not unexpected. But as we add constraints, that is hypothetical what if physics scenarios at locations within the envelope, the degeneracy dissolves. And once it dissolves, you can use that plot of the action as a litmus test for the correct solution to save a lot of time. Sorry about that. In addition, you can also very efficiently rule out certain huge parameter spaces by just simply looking at whether the path of least action is found by any of the paths that search those particular regions. Okay, so it's in this way that we are optimistic that these techniques, this technique has the power to augment existing codes and save a considerable amount of computation time. So up next, I'm going to be very brief with this. I'm only going to comment on the bold. Eventually, we want to add backscattering to the problem, right? We can still solve our problems with forward integration, but we need a lot more confidence in our optimization technique before we let it lead us blind to learning about new physics. Alrighty, so that's it for the neutrinos. Again, as I said, Douglas told me before I planned my talk that I should aim for a very broad audience here. So I would like to demonstrate to you how versatile this inference technique can be. I've applied it in the past few years to a range of other topics that I'd love to share with you now. Let me just grab a drink of water. About 4 years ago, I posted on the preprints server, the archive, a study using artificial neural networks. Now, artificial neural networks are a type of machine learning that do very well when trained using very large data sets. So we're no more sparseness. We're into the realm of very, very large, dense data sets. So let me just summarize for you just with the abstract, what I did to give you a flavor for it before I delve into details. It's called a neural networks approach to predicting how things might have turned out had I mustered the nerve to ask Barry Cottonfield to the junior prom back in 1997. And let me just summarize it, just read a bit of the abstract here for you. We use a feed-forward artificial neural network with backpropagation through a single hidden layer to predict Barry Cottonfield's likely reply to this author's invitation to the Once Upon a Daydream junior prom at the Conard High School Gymnasium back in 1997. We'll skip a little bit, I'll skip down to here. To simulate Berry's inability to learn efficiently from large mistakes, an observation well documented by his algebra teacher during sophomore year, we choose a simple quadratic form for the cost function so that the weight update magnitude is not necessarily correlated with the magnitude of output error. Network performance on test data indicates that this author would have received an 87.2 with an uncertainty of 0.1% chance of yes, given a particular set of environmental input parameters. Most critically, the optimal method of question delivery is found to be secret note rather than verbal speech. There also exists mild evidence that wearing a burgundy mini dress might have helped. The network performs comparably for all values of regularization strength, which suggests that the nature of noise in a high school hallway during passing time does not affect much of anything. We comment on possible biases inherent in the output, implications regarding the functionality of a real biological network, and future directions. Overtraining is also discussed, although the linear algebra teacher assures us that in Berry's case, this is not possible. So here's Berry from my yearbook in 1997. Isn't he a dream? So I'm going to add a caveat here that by most historical accounts, Berry Cottonfield was a brash and unprincipled individual with extremely below average learning capabilities, and the association, the unprovable association, mind you, with the serial disappearances of various neighbors' cats. But let me tell you, they didn't know him like I did. From the moment I first laid eyes on this guy across the seesaw in second grade, I was smitten. I was sure that he was a mysterious, multi-layered, deep soul with perhaps latent, unstable inclinations. I was determined to figure him out. I peppered him with questions about, his essence, his deepest urges and desires, every chance I got, most often during passing time between classes at Conard High School in West Hartford, Connecticut. And this ultimately culminated in a 5-volume diary, very densely sampled diary. I admit I was a bit obsessive looking back on it. But I never mustered the courage to ask Berry to the junior prom. I've regretted it, and while innumerable poems have been composed on this topic, no quantitative study has ever been looked into. I wondered what he would have said. I just wanted a maximum likelihood answer. Now, you might suggest, well, why don't I just pick up the phone and call him? Well, that was no longer a possibility because it would have violated my restraining order. So the only possibility left to me really would be to look at this 5-volume diary, again, a very densely sampled data set, and ask, well, could this serve as a kind of proxy for Berry's personality? That is there sufficient information in these measurements to predict backwards, like I'd done with the neutrinos? That wasn't much of a problem. All right, so let's give this a try. So now I turn to the black art of artificial neural networks. Now, as I said, this is a type of machine learning, and it's where you create a neurobiology-inspired architecture by exposing it to training data, very dense, large sets of training data. And you build this thing that can mimic the ability of a real brain to categorize information. There's a decades-long history of these kinds of things. Now, these algorithms are actually astoundingly stupid by human standards, and actually by sea slug and fruit fly standards. That's also well documented in the literature. But nevertheless, they can learn to be stupid rather quickly, and thereafter serve as a very powerful predictive tool. Now, further, the very nature of these algorithms parallel Berry Cottonfield quite readily. They're multi-layered. They have connectivity among the layers and the nodes in the layers that may yield unstable or erratic or nonsensical output. Relatively low intelligence, powerful, but very, very limited utility. Okay, so these seem to me at the time to be well suited for creating an artificial Berry and examining its decision-making strategies. Okay, let me show you how this goes. We use a two-tiered learning approach here. Okay, so let me explain to you first the first stage. It's called brain becoming Berry, or creating a 0th order approximation to Berry. This is stage 1. This is your typical, very simple layout of an artificial neural network. You have 3 layers here. The first layer is your input layer. This is the layer in which you stick your training data, whatever it might be. Then there's an output. And if you know the desired answer, then you can measure the error in the output. So you can create a cost function that represents the error in output. In the middle is the brain. So this is the invisible part. We call it the hidden layer. In this model, there's only one hidden layer. You can have more than one. And then the lines, the black lines and the purple lines, these are what in neuroscience parlance people call the synapses between the nodes or the neurons. And in stage 1, what we seek to do is set bare bones Barry, just who he is, just his bare essence. And we're going to adjust the synaptic weights according to minimizing the cost function, the output, because we know the answers. For example, the questions are something like, is your name Barry? Do you have a dachshund named Raskolnikov? Questions that have a definite answer that he should know. And what we do is the input goes into node 1 of this input layer, just node 1. The other ret squares are left alone for the moment. And what we do is we seek to tweak this, the synapses coded in purple are the synapses that are active during stage 1. And we seek to tweak their weight so as to minimize the output error. Okay, so that's stage 1. I should add a caveat that the aim to minimize output error is not squarely consistent with Barry's behavior in a classroom setting during exams, for example. To mitigate this bias, we use a quadratic cost function like the one I showed you in the first half of this talk. It's actually terrible at learning efficiently from large mistakes. So in that way, we hope to capture Barry's ability to answer very simple questions. Okay, so that's stage 1. Stage 2 is the fine tuning. So in stage 2, we input into the other 9, I forget how many there are here, looks like 9 or 8, other input nodes, environmental input parameters, such as, what time of day it is, whether Barry's eaten lunch yet, whether Barry's recently had a fight with his annoying kid sister, Janice. And the questions that are delivered during this stage they're a little bit more complex. They require a decision to be made. A decision such as, can I borrow $1? Can I borrow $5? And we ask them these questions over all sets of possible input parameters, and we choose the set of parameters, importantly, that requires the least amount of tweaking of the synapses that were already set in stage 1. The idea being that Barry now already knows who he is, artificial Barry. To change that would be undesirable. It would be kind of like barking up the wrong tree. Now, I should make one note about the global minimum that was an object of such high interest during the first half of this talk. In this scenario, the solution is highly unlikely actually to be the global minimum, but a local solution will suffice for our standards, provided that our standards are sufficiently low. So finally, what we do is we ask, will you go to the prom? And by now we assume that he is trained to understand who is asking the question. And as I showed you in the opening slide with the abstract, pretty good result here, 87.2% success rate. Pretty happy with that. A couple comments on this result. We had adopted the results from the training scenario in which Barry had not recently fought with Janice. We found that yielded a much greater stability of the output answers, and 10 times less tweaking of the weight set in stage 1 were required. Some other notes on the optimal parameter values. Question delivery method. Secret note was favored over verbal speech at a considerable percentage. The outfit, burgundy mini dress won out slightly over other shades of mini dress, while the mini dress category overall beat 726 other wardrobe choices. And the remaining 134 environmental parameter choices had negligible effect on the outcome. A couple topics for future discussion, perhaps. Overtraining. Overtraining is a problem in machine learning where your machine learns the noise in addition to the data. So there might be noise in your data, there might be noise in the connection between the machine and the data, the means by which the machine receives it. That's not good. So what you can do about that is include what we call a regularization term in the cost function. Low regularization, if you're not regularizing at all, you're allowing the machine to learn the noise quite easily. High regularization, you're prohibiting that. So we found that the network performs comparably for all choices of regularization strength, indicating that the nature of noise in a high school hallway during passing time doesn't really seem to register with Barry. We're not sure what the scientific implications of that are, but they do seem consistent with the algebra teacher's comments that overtraining is not a concern where Barry is concerned. Oh, a memoryless system that learns. Okay, so this neural architecture is a feed-forward only Markov chain. Input, information from input goes to middle, goes to output. There's no feedback flow of information. So the system has no memory. This might explain a couple strange findings we had. Barry learned very quickly such questions as, do you have 10 toes? But there was no convergence, interestingly, on the question, will you have 10 toes tomorrow? So this problem might be indicative of the difficulty inherent in trying to teach a memoryless system to learn anything. One solution might be to add feedback. Most of us have memories, or at least we're under the impression that we do. Oh, and finally, future directions. I know a talk is always supposed to end on exciting future directions. But while the output of artificial neural networks does not necessarily provide the right answer, I am pretty enamored of this one. So I take it to be right, and I plan no future directions. So, oh, right. I think I've crammed in quite enough already, but I did promise this in the title, and lest I be accused of false advertising, just one last slide. I also looked into an artificially intelligent means to escape discreetly from the departmental holiday party. It's a guide for the socially awkward. We are in development with an algorithm that can help you escape from an extremely unsavory situation. For example, this horribly claustrophobia-inducing scenario you see pictured here, a 2-bedroom Manhattan apartment crammed with your colleagues during a drunken holiday party, and there are multiple means of exit, and we are developing an inference procedure to help you figure out which one to use. There, I will end there, and I want to thank my collaborators, Amol Patwardhan and Ermal, who forbids me from even trying to pronounce his last name. These are postdocs in neutrino flavor evolution. Barry's not a collaborator, but as I'm sure you can tell by now, he's been inspirational to me throughout my years in science. George Fuller, who has been an inspiring mentor and collaborator and knows neutrino flavor evolution like the back of his hand. And my very talented undergraduate students at New York Institute of Technology, Armand Amitage and Mary Sanchez. And thank you all so much for listening. The end.
Thanks, Eve. Let me offer you applause. And we turn to questions. So who wants to jump in with a question? Oh yeah, okay. Elisa, do you want to unmute?
Hi, sorry. Should I turn my video on as well here?
Sure, yeah.
Okay, sorry about that. I was wondering, when, like you were saying that every time a neutrino interacts with matter, its path changes. So I was just wondering how the modeling takes into account all of the interactions that would happen once the neutrino sort of hits Earth's atmosphere, because that would completely scatter the path.
Oh, for a neutrino, the atmosphere isn't even, a good question. The atmosphere isn't even there, or it may as well not be. So let me repeat, I think an example I gave in the very beginning is your hand to a neutrino is nothing. The core of the Earth to a neutrino is nothing. So in order to see neutrinos interact appreciably with matter, you've got to get to the densities surrounding the core of a neutron star inside a core collapse supernova. That's one example. And to give you an idea of the density there, think of collapsing the sun into the size of Vancouver. these are the densities that are required for neutrinos to interact significantly with matter. So the atmosphere of Earth is not going to hinder them.
That makes a lot of sense. Thanks.
Thanks for the question. I know I threw a lot at you, so I'm not surprised that you've forgotten one particular thing.
The question and the bird song, which is always nice to hear. Catherine.
Yeah, I was just wondering, like, what was the best way to escape from the Christmas party?
It depends. It depends on many factors. You've got to assess how many people are there, for example. The more people who are there with you, the easier, because the less attention people are paying to you specifically. You've got to pay very keen attention to locations such as the punch bowl and the dance floor maybe, and keep an eye on which exits seem to be more sparsely populated. Keep a careful eye on them and calculate how much time you need to get there and make a quick and safe exit without being seen. So it's very dependent on the immediate ambient environment. It's a very dynamical system, hard to predict very far in advance. Thank you for that question.
It's interesting how,
that was cool.
how the modern world has changed things, right? So you're talking about this crap.
I came out with that paper, or I wrote that paper a week before we shut down.
I mean, how I can't even picture what it's like to be in a room with two other people, let alone, I just can't even conceive of that. How does that work?
That was completely unintentional. I never would have written that paper had COVID happened a few weeks earlier.
So it was your fault.
I guess, yeah. Yes, blame me.
More questions for Eve. Kevin, do you want to unmute?
Hi. Thanks for the talk, Eve. I'm pretty interested in the statistical data assimilation. Could you provide any more comments or applications of where else it could be used in physics or even neuroscience in your experience?
Oh, absolutely. I guess I could go. I don't know. Let's see, we can go back to that region in case there are specific slides you've got questions on. Sorry, is your name Kevin?
Yes.
Yeah, hi. So it's an extremely versatile technique. It was born in weather prediction, taken to neuroscience, then taken by us, my group with George et al. Into neutrino physics. But it can be taken anywhere you have a reasonable idea of what your underlying model is, and where you're trying to reconcile that model with available measurements. So you've got a dynamical model written in ODEs or PDEs, what have you, and then you've got measurements you want to, and your model's incomplete. There are perhaps parameters of it that you don't know, that you would like to be able to estimate. And your goal here is to be able to fit existing data, but critically be able to complete your model so that it can predict successfully future data that you do not have yet, that you have not used in order to build the model itself. It can be applied to, and I'm speaking literally here, any system that can be formulated as a dynamical model. And that will, at some point in the future, I imagine, have, even if you don't have available measurements now, you can learn a lot from inventing them in simulations. You can, rule out theories that probably are not ever going to pan out and home in on those that seem more fruitful. So as far as I know, so far, just the geosciences, neuroscience, and now astrophysics, I believe, are the only areas in which DA has been applied. I could be wrong about that.
Right. Is there any, thanks for the answer. Is there any assumptions on the data that you need to use with SDA? Like when you say that you have a dynamical model and then you need measurements, are there any assumptions on the measurements or just any data?
Oh, so you're assuming that, I should give you an example. Say you have a model for how the sun shines. And one of the variables in your model is intensity. of the light that's emitted from the star.
Mm.
Okay? You can measure intensity. So what I'm trying to say is the measurements that you're making must correspond somehow to variables within your model. See what I mean? So if your
Yes.
model, okay, so if you measure intensity, but your model has nothing to do with intensity, well, that's useless.
Sure.
But maybe the measurement isn't intensity exactly. Maybe it's a very noisy measurement of intensity, for example.
Right.
Maybe
Right.
so sometimes you, in your cost function, so you want to minimize the difference between what your model state variable and the measurement. But sometimes it's not just a one-to-one. Sometimes there's a yeah, right. Okay. So a transfer function between the measurement and its representation within the model.
Right. Okay. Cool. Yeah. Thank you. Thank you so much.
Great. Sure.
One of the criticisms of machine learning by non-machine learning people is uncertainties. So does SDA have a similar disadvantage? And is it challenging to get reasonable uncertainties out?
Well, I'm assuming you're talking about dealing with real measurements as opposed to simulated. Yes. So one thing I left out of my final slide with the neutrinos problem is one next step is we want to do a very detailed study in simulations of the procedure's sensitivity to noise before encountering a real signal. Because if you haven't thought about that, you encounter a real signal. Well, what in the world is that going to correspond to in terms of your model? Yeah. So depending on the model, depending on the data, your outcome can be highly sensitive to contamination. And it's very important to get a handle on what that looks like in simulations prior to dealing with real data, which are a monster compared to simulations, because in simulations, you know the answer at the end of the day. So you know how well, it's a way to test how well your procedure can be trusted before unleashing it on real data.
Okay, we could talk more about that later maybe, but there's a question from Christy.
Oh, hi. Yeah, I was just curious about like those subsections that you had, like how you determine that.
Sorry, subsections, and are we talking about neutrinos or?
No, I meant like with the whole like prom date scenario, like the dress color and like the delivery method.
Oh, okay, cool. Yeah, let's go back there. Yeah, so in the second stage of training, Barry, and of course, I didn't actually do this, but you can use this technique on, in a realistic situation. You want to identify, so you have input parameters in your, outermost or your input, sorry. You're inputting environmental parameters and seeing what the impact is on the effectiveness of the learning. So in this particular situation, I illustrated that by saying, we want to pick the set of input parameters that yield us the desired answer. So we're tweaking, these purple lines here are the weights among the nodes in the network. And what you do in training these artificial neural networks, what you're doing is, and I'm not just joking here anymore, you are adjusting the weights. And in the language of neuroscience, if these were neurons, the synapses or the arms that connect them, you're adjusting the strengths of those weights in order to get the output that you want. And depending on the environmental input parameters that you kind of put your artificial brain in, that will go differently. You want it to go as easily as possible, but the environmental input parameters in that way are affecting, in some sense, the way in which the algorithm is interpreting the questions that you're delivering. Is that, I'm not sure if that answers your question.
Yeah, no, it did. Thank you.
Okay, great, sure.
Yeah, it's the whole Barry Cottonfield thing. It's like it's almost like a paradigm for how you do machine learning. It's almost like if he didn't exist, that you might have just made the whole thing up in order to illustrate machine learning. It's almost like that.
That was my hope, to actually teach people how this actually works by applying it to absurd problems. You know, I actually had one college professor, I felt terrible. He emailed me for the data. He wanted to give it to his students to reproduce. He thought it'd be fun to have his students reproduce the work in his classroom. I felt terrible telling him, there are no diaries, man, I'm sorry. that part was not true.
You burned the diaries, presumably. No, anyway, I really like this slide because it's a very good teaching moment for, because often it's incredibly abstract when you read the hardcore machine learning papers and you can't figure out what on earth they're on about because it's so abstract, right?
Well,
So this is great. Yeah.
Thank you. I really appreciate hearing that feedback. I would really like to do this. I had my non-science friends actually read it, and now they know a little bit about machine learning, where they would never read my neutrinos papers, right? So I think this really can be developed into a teaching tool. I'd love to do that over the long term.
Yeah, maybe enthusiastic undergrad could invent the data.
Great.
Right. That would be cool, actually. More questions? Are we really out of questions? I've probably asked enough. I should stop and we could just we could break. I feel like we've taken up enough of your time anyway. Let me give people one. Oh yeah.
Excuse me, sorry.
was that?
It's Elisa here again.
Yeah, sorry.
I do have another question, though it's not actually related to the conversation of the talk necessarily. I didn't want to waste people's time with it if everybody needs to get going. But,
no, go ahead.
I was wondering, actually, I also have a background in theater as well as physics, and I was wondering how you've personally combined those.
It is my dream to finally combine them.
That's a great question, by the way. So you don't need to apologize for asking such a good question.
Yeah, it is a great question. So, so two answers. One is, for the most part, I've been just hopping between the two. But I would love to ultimately connect them. There's one exception. I took a break from graduate school for a few years and founded a theater company. And one thing we did was create a science educational sketch comedy show. And that was a whole lot of fun. We did it for, we toured to schools. We did it actually for nightclub audiences in Midtown. Well, at least drunk adults thought it was funny and fun. I really would love to do more of that. Only, actually, this past semester, I finally was able to make time in my class. So I've been teaching electricity and magnetism this spring at New York Institute of Technology, and I carved out a little time to devote one entire class to improv games. And that was so much fun. I'm building towards something. I'm really not sure what yet. But it is high. Ultimately, that's what I want to spend most of my time on. I love the idea of using improvisation, theater, and specifically comedy to teach.
Thank you so much.
Yeah, thank you for the question.
Yeah, maybe you should get together and figure out how to do that over Zoom, right?
Email me. We can talk more, please. Here, wait.
Lucas. Yeah. Oh, sorry. Is Elisa back?
I just put my email up.
Okay. Lucas.
Hi, Eve. I just had a quick question. Thank you so much for the talk. It was great. I just want to know, if I'm not mistaken, you mentioned earlier in your talk that the goal of your neutrino model was to get a better understanding of where within the supernova the MSW resonance occurs. And it was my understanding that the MSW resonance is where neutrinos have the maximum probability to change their flavor. So I kind of just wanted to know what would be the importance of determining where exactly that point is.
Oh, great question. So we have been working with a very, very toy small scale model just to get a sense of whether optimization is going to be good at probing these questions. So we asked a very, very simple question: where does that resonance occur? Because expand that to a much, much more complicated scenario where you want to know how the flavor changes at every location within that cloud. There may be multiple MSW resonances. There may be multiple shocks within the envelope. It's a very, very complicated picture. And we're only scraping the surface. I mean, it's a cartoon Mickey Mouse model we're working with. So that question, where does the MSW resonance happen, is just a cartoon. It's like a placeholder for a question that we could ask when we scale the model to a much larger size and ask a set of much more complicated questions. What is the flavor field? So there's not just one transition. What is the very, very complicated evolution history that occurs throughout the envelope? So it's just a bare bones ground zero question leading up to bigger and better things, we hope.
Perfect. Thank you so much.
Sure. Thanks, Lucas.
Okay, let me ask again if there's any further questions. If not, we should all thank Eve again for giving up her time and giving us a great presentation here.
This has been a delight. Thank you so much.
Yeah.
This is my first spoof talk ever. I'm thrilled.
That was a spoof talk. What?
Oh, sorry, I got it away. Oh, damn. Should've
What?
said-
We can start recording, Riley.